Good afternoon to all of you. I welcome all the technocrats here for this webinar. Yesterday I have discussed with you the basic concept of the memristors. And my basic idea is that I am going to use this memristor concept as well as chaos theory in the communication system with the basic aim for a secure communication engineering. Nowadays security is the foremost in communication engineering. So the data cannot be stolen at the transmitter level, neither it can be at a media level, or nor it may be copied at a receiver level. So yesterday I discussed with you the basic concept theory about the memristor, and today I will start with this chaos, and after this as the content shows from memristor to chaos, and then I will implement this memristor and chaos in a communication system in such a manner that in communication system security plays a foremost role. So now let's start with the chaos. A very renowned engineer and an equally scientist, Phillips Marillès, has stated, does the flap of a butterfly's wing in Brazil set off a tornado in Texas? And it was strange when he quoted this statement. Again, there is a one Hindi movie, you might have seen that Hindi movie, its name is Raj. And number of times the line has been repeated. The line goes like this, जब कभी तितलियां पंख फड़फड़ाती हैं तो दूर कहीं समुद्रों में तूफान आता है. What does it mean? It means when the initial conditions are disturbed or changed, the overall concept also changes. And here we start with a chaos. Chaos is basically not a technical word. It is an English dictionary word which means disorder. And technically it appears to be a random and disordered. But actually it is a deterministic in nature, and it means it is precisely controlled by natural laws. It is precisely controlled by the natural laws. Chaos theory is the qualitative study of unstable aperiodic behavior in deterministic nonlinear dynamical systems. Aperiodic behavior is observed when there is no variable describing the state of the system that undergoes a regular repetition of values. Unstable aperiodic behavior is highly complex. It never repeats and it continues to manifest the effect of any small perturbation. A chaotic system shows sensitivity to initial conditions. That is why weather is so difficult to forecast. The theory has been applied to business cycles and dynamics of the animal population, fluid motion, planetary orbits, electrical currents in semiconductors, and medical conditions and the modeling of arm ratios. If we take the basic concept of the chaos, we have to peep into its history. Henry Poincaré is termed as the father of chaos theory. He has formulated this concept in 1960. Significant and more practical work was done by the Edward LORENZ in this field during these years. The name chaos was coined by Jim York, an applied mathematician at the University of Maryland. Pierre Berge, U.V. Pomey, and Christian Vidal have explained the basic concept of chaos in their book. This book is an introduction to the study of dissipating dynamical systems. It deals with the detailed aspect of chaotic theory involving strange attractors, bifurcations, and synchronization of oscillators. Further, Taylor has utilized ideas and techniques of chaotic dynamical system to obtain a refined analysis of behavior of control systems. Starting from the definition of chaos, he has dealt with the stability and stabilizability of the control system. Thus, basic idea of chaos control and chaos system in digital feedback system also have been presented. Further, Cross and Jodel has given a set of program to practice the use of computer in the field of nonlinear physics and chaos. And they have described a new mathematical idea in nonlinear dynamics in a way in which engineers can apply them in real physical systems. He has presented several examples of chaotic behavior in mechanical engineering, chemical engineer, chemical reactions, electronic circuits, electrical circuits, civil engineering problems, and fluid dynamics. In geometry, linearity refers to Euclidean objects like lines, planes, three-dimensional space, etc., etc. These objects appear the same no matter how we examine them. In non-linear object, a sphere of example looks different on different scales. When looked at closely enough, it looks like a plane, and from a far enough distance, it looks like a point in algebra. We define linearity in terms of the function that, as stated, that x plus y is equal to fx plus fy, and f(ax) within bracket is equal to af within bracket x. Non-linear is defined as the negation of the linear. It is a negative part of the linear is termed as the non-linear. Non-linear is defined as the negative part of the linear. For a linear system, if we have two zeros, for example, if we take fx is equal to 0 and fy is equal to 0, then we automatically have a third zero, that is f within bracket x plus y is equal to 0. In fact, there are infinite many zeros as well, since linearity implies that f within bracket ax plus by is equal to 0 for any a and b. This is called the principle of superposition. It gives many solutions from a few. Linearity is rather a special and no model of a real system is truly linear. Some things are profitable studied as linear approximations to the real models. The example, the fact that Hooke's law, the linear law of elasticity, which is a strain is proportional to stress, is approximately valid for a pendulum of a small amplitude, implies that its period is approximately independent of amplitude. However, as the amplitude gets large, the period gets longer. A fundamental effect of non-linearity is in the pendulum equation. An infinite dimensional nonlinear model can be turned into an infinite dimensional linear one. Secondly, nonlinear systems have been shown to exhibit surprising and complex effects that would never be anticipated by a scientist trained only in linear techniques. Prominent examples of this include bifurcation, chaos, and solitons. Nonlinearity has its most profound effects on dynamical systems. We currently have no general techniques, or you can say we have just a few special ones, for telling whether a particular nonlinear system will exhibit the complexity of chaos or simplicity of order. Thus, since we cannot yet subdivide nonlinear system into proper subfields, it exhibits a whole. Nonlinear sciences has application to a wide variety of fields, from mathematics, physics, biology, and chemistry to engineering, economics, and medicine. Now, this is the dynamical system term. It will be used number of times for this explaining the chaotic concepts. So I just want to review it, that what actually the dynamical system we will refer in a chaos theory. A dynamical system consists of an abstract space or a state space whose coordinates describe the dynamical state at any instant, and a dynamical rule which specify the immediate future trend of all state variables, given only the present values of those same state variables. Examples are Maxwell equation and Stokes equation, and other equations are also there. Mathematically, a dynamical system, if we say mathematically we want to define dynamical system, or we just give the basic idea that what the dynamical system is, it can be like this: a system, an initial value problem. Mathematically, a dynamical system is described by its initial value problems. Dynamical systems are deterministic if there is a unique consequent to every state, and they are stochastic or random if there is more than one consequent chosen from some probability distribution. It means just like this, the perfect coin toss has two consequents with equal probability for each initial state. Most of the nonlinear science deals with the deterministic systems. a dynamical system can have discrete or continuous time. Now, as per this phase space, this term is also used commonly for a chaotic theory for its explanation. A phase space is actually it is a collection of possible states of a dynamical system, and a phase space can be finite. It's just like for the ideal coin toss, we have two states, head and tail. So we can say that phase spaces can be finite, countable, infinite, and just like state variable are in integers, or uncountably infinite, just like state variables are real numbers. Implicit in the notion is that a particular state in phase space specifies the system completely. It is all we need to know about the system to have complete knowledge of the immediate future. Thus, the phase space of the planar pendulum is two-dimensional, consisting of the position, that is angle, and velocity. If we refer to Newton, according to Newton, specification of these two variables uniquely determines the subsequent motion of the pendulum. The path in phase space traced out by solution of an initial value problem is called an orbit or trajectory of the dynamical system. If the state variable takes real values in continuum, the orbit of the continuous time system is curved, while the orbit of discrete time system is consequence of those points. These attractors are, this term is commonly used for the explaining the basic concept of the chaos theory. Attractors is simply a state in which a system settles, means thus dissipation is needed. Thus, in the long term, a dissipative dynamical system may settle into an attractor. I repeat, a dissipative dynamical system may settle into an attractor. So, attractor is a set in the phase space that has neighborhood in which every point stays nearby and approaches the attractor as the time goes to infinity. The neighborhood of points that eventually approach the attractor is the basin of attraction for the attractor. Attractors can be simply such as a point. Another example of an attractor is a limit cycle, which is periodic orbit that is attracting. Just like limit cycle can also be repelling. More surprisingly, attractors can be chaotic. The boundary of a basin of attraction is often a very interesting object, since it distinguishes between different types of motion. Typically, a basin boundary is a saddle point, a crisis in the change in an attractor where its basin boundary is destroyed. An alternative definition of attractor is sometimes used because there are systems that have sets that attract most, but not all. Initial condition in their neighborhood, such as phenomena, is sometimes called the riddling of the basin. Thus, an attractor is defined as a set for which a positive measure, you can say probability, of initial conditions in a neighborhood of asymptotic to the set. Now next is a fractals. This term is also required to be understood so that the theory should be clear in your mind. Fractals appear everywhere in the study of a dynamical systems, and they consist of four main characteristics. Number one is a fractal is a geometric object which can be divided into parts, each of which is similar to the original object. They possess infinite detail and are general is self-similar. By seeing from one side, the fractals cannot be distinguished. They look like to be same, all the fractals, but actually there are a bit difference between them. They can often be constructed by repeating a simple process. They have a non-linear, they have a non-integer dimensions. These are the few properties of the fractals. Kindly pay attention to this scientist photo. He is Poincare, the father of chaotic theory. He is termed as the father of the chaotic theory. he have given this idea of the first of all about the chaotic theory, that what chaotic theory is Henry Poincaré, and he have formulated this in 1960s. And the question arises, how did he got the idea of the chaos? The idea of the chaos, it just happened with a very small events. He was working on a weather forecasting with a number of computers, and he just want to predict the weather forecasting. For a cup of coffee, he went to another room, and when he came out, when he came back after few time, he found out the results are entirely changed. He was astonished how it happens. Then he again restarted the system, and he find out that the change has been made due to the minor verification, minor change in the initial conditions. While he was just getting from his chair, he might have disturbed the setting of the system to the 3 decimal, 4 decimal, or you can say initial conditions. From here he got the basic idea of the chaos. As it happens that a small difference in the initial state of the system can lead to a very large difference in its final state. A small error in the former could then produce an enormous one in the latter. Prediction became impossible, and the system appears to behave randomly. Now this definition is concerned. As per the definition part is concerned, as per the chaos is concerned, different definitions are available, and these definitions, none of them definition is complete, and neither they are missing something. But these 3 famous definitions or the quotations by the very renowned scientists who have worked so much on this chaos theory. First one is given by G.W. Flack, and third one by G.P. William, and second one is by G.P. William, and third one by E. Lorenz. In fact, at the later stage, Lorenz scientists have worked so much on a chaos theory. E. Lorenz states the property that characterizes a dynamical system in which most orbits exhibit sensitivity dependence. I repeat, the property that characterizes a dynamical system in which most orbits exhibit sensitive independence. So it means that what it is. It has been said that chaos is a name of any order that produces confusion in our mind. As in the very starting I told you that chaos as the English dictionary word which means disorder, and technically it is not that like this. So chaos is a name for any order that produces confusion in our mind. However, the mathematical definition maybe goes like this, or the mathematical definition of chaos is like this. Chaos is effectively unpredictable long-time behavior arising in a deterministic dynamical system because of sensitivity to initial condition. I repeat for your kind attention. Chaos is effectively unpredictable long-time behavior arising in a deterministic dynamical system because of sensitivity to initial conditions. It must be emphasized that a deterministic dynamical system is a perfectly predictable given perfect knowledge of the initial condition, and as in practice always predictable in the short term. The key to long-time unpredictability is a property known as sensitivity to initial conditions. For a dynamical system to be chaotic, it must have a large set of initial conditions which are highly unstable. No matter how precisely you measure the initial conditions in the systems, your prediction of subsequent motions goes radically wrong after a short time. Typically, the predictability horizon grows only in logarithmically with the precision of measurement. Thus, for each increase in precision by a factor of 10, say we may only be able to predict 2 more time units measured in units of Lyapunov time, the inverse of Lyapunov exponent. More precisely, if we say precisely after referring all these definitions and the previous slides. If just in a summary, if we want to have a clear-cut definition of the chaos, then it would goes like this: a system which has closed invariant set. Means more precisely, chaos is a system which has a closed invariant set is said to be chaotic if it satisfies three conditions. A system which has a closed invariant set is said to be chaotic if it satisfies three conditions. Number one, the set of a periodic point is defined. Number two, there is an orbit which is dense. Third, there is a sensitive dependence on initial conditions. Extreme sensitivity of chaotic system to initial conditions once led to the expression that chaotic motion is in general neither a predictable nor controllable. However, recent research efforts have shown that not only prediction but also control of chaos are possible. It is now well known that most conventional control methods and many special techniques can be used for chaos control. Similar to conventional system control, the concept of controlling chaos is first to mean suppressing chaos in the sense of stabilizing chaotic system response. Chaos control targets are better managing the dynamics of nonlinear system on a wider scale, with the hope that more benefits may thus be derived from the special features of chaos. Control of chaos is necessary because firstly a chaotic system response with little useful information content is unlikely to be desirable, and secondly chaos can lead system to harmful or even catastrophic situations. There is sometimes one more question rises in the mind, that whether this chaos can computer simulate the chaos? Sometimes this question comes in the mind. Strictly speaking, chaos cannot occur on computer because they deal with a finite set of numbers. Thus the initial condition is always precisely known and a computer experiments are perfectly predictable in principle. In particular, because of the finite size, every trajectory computed will eventually have to repeat, as thus be eventually periodic. On the other hand, computer can effectively simulate chaotic behavior for quite long time, just as long as the discreteness is not noticeable. I just want to repeat this line again. It carries a great meaning and it will help you to understand that what I am just going to explain you about the chaos theory. That in particular, because of the finite size, every trajectory computed will eventually have to repeat. On the other hand, computers can effectively simulate chaotic behavior for quite a long time within a condition, just so long as the discreteness is not noticeable. And minimum space dimension for chaos is slightly confusing topic, since the answer depends on the type of the system considered. First, consider a flow or system of differential equation. In this case, Poincare theorem tells us that there is no chaos in one or two dimensional phase space. Chaos is possible in three-dimensional flows. Standard examples such as the Lorentz equations, which I am going to discuss in my next few slides. And these are the mathematically 3D flows that are probably chaotic. If the flow is non-autonomous, then time is a phase space coordinate. So a system with two physical variables plus time becomes three dimension and chaos is possible. Within a bracket, I would like to state forced second order oscillator do exhibit chaos. Forced, I am laying a stress on the word forced, F-O-R-C-E-D. For homomorphism, we must have at least two-dimensional phase space for chaos. This is equivalent to the flow result, since a three-dimensional flow gives rise to a two-dimensional homomorphism by a Poincare section. Now a very renowned concept, the terms which is just you can say very well used for a chaos theory. And if we want to understand this chaos theory, we have to understand the butterfly effect. This butterfly effect was first of all term coined by E. Lorenz. And I would like to state a very renowned scientist who have worked remarkably in chaos theory, that is Phillips Maryllis. Thus the flap of a butterfly wings in Brazil, set of a tornado in Texas. It means just like in Hindi movie Raj, the line was there, जब कभी तितलियां पंख फड़फड़ाती हैं तो दूर कहीं समुद्रों में तूफान आता है. And actually, if you refer any religious books, whether it is a Mahabharata, Gita, Bible or Quran Sharif or other what happened? Should I continue or? Huh? They will call me. I should wait. Yeah, I should continue.
Hello.
Hello?
Yes, sir. Please continue. Show your screen.
Okay. I am seeing the screen. Should I continue?
I can't see your screen yet, sir. Just 1 minute, sir.
They are not able to see the screen.
Yes, sir.
I am a computer engineer sitting with me. He is helping. They are not able to see the screen. Just he is setting it. Switch it off or again switch it on. Can you? Is it now? Are you seeing the screen?
Not yet, sir. Yes, now I can see, sir.
Should I continue? Hello? Should I continue?
Turn off the camera and continue, sir.
Camera, turn off the camera. Switch off the camera. Okay. Leave it. Now is it all right?
Yes, sir.
So I am talking about the butterfly effect. Sorry for the disturbance. And I have just narrated a story and how it come about. That is the basic story, that initial condition changes, the things changes at a very fast speed. Now this is the butterfly effect by Lorenz. Then Lorenz had entered the initial condition with a three decimal place precision, considering the difference of one part in 1000 negligible. Normally we do it like this. For example, if I take 1.9876, so what we do, we simply round it off, 1.9876. 988. We do it like this, or sometimes we say 1.987. We left the rest part of it. We thought it is a negligible, and he was working with these conditions. But after when the butterfly effect was, this effect was coming idea and it was born, then they thought it, they make it clear that we cannot neglect. We have to take the complete concept because the initial conditions make a drastic change. But overall with this, there are two things happens with this experiment. A sad ending is, in view of the inevitable inaccuracy and incompleteness of weather observations, precise very long range of forecasting would seem to be non-existent. This is the butterfly effect. The idea they have got, the LORENZ, the things is clear that it cannot be for a long range forecasting. But the happy ending is LORENZ attractor, emblem of chaos theory, is born, and with it a whole new scientific field that is still very active today. With this, all the researchers, they confess that in coming time, this concept, this LORENZ attractor will play a very, very vital role in a research work, and it will find out the number of unlimited applications in multidisciplines. Chaos theory is not limited to electrical and electronic engineering. It is proved nowadays, the work is going in the civil engineering also, mechanical engineering also. For technical, next 2 decades goes to this theorem. In communication engineering, here I would like to state in a coming time, there will be a new subject, that is chaos communication engineering. And in communication, chaos is going to play a very, very important role, and that just in a coming slide I will try to explain to you. When the LORENZ was working on a weather forecasting, as I explained to you, and the incident also I explained. Now these are the LORENZ equations. Equation seems to be very simple. And with these equations, LORENZ designed systems, attractor. Now kindly pay attention to these attractors. These attractors seems to be similar at very one go. But actually they are not similar. You will find out there is a difference of a very, very small initial conditions, and due to which these are separate with each others. Now the essence of chaos. With LORENZ work, now the concept comes out, a dynamical system entirely determined by its initial conditions. It means deterministic. Another fact, but which evaluation cannot be predicted in the long term. That is the limits. First one is a happy, second one you can say sorrow ending. First one is the main advantage, new concept comes to the researcher, and second one, with this advantage, the limitation also comes. And limitation is that it cannot be predicted in the long term. Now is dependence on the initial conditions. Here, you kindly pay your attention, I have taken the comparative studies. First one is a regular process, and in this diagram, you pay your attention, you will find in front of the regular process there is a chaotic process. And in normal cases, the initial condition is only one. But here you will find out many values within an error bound. And in initial condition, here the process is determined by the dynamic equations. Here the process is determined by the dynamic equations. To understand these initial conditions, consider a boulder precariously perched on the top of an ideal hill. The slightest push will cause the boulder to roll down one side of the hill or the other. The subsequent behavior depends sensitivity on the direction of the push, and the push can be arbitrarily small. Of course, it is of great importance to you which direction the boulder will go if you are standing at the bottom of the hill or one side or the other. Motion on an attractor is chaotic if it displays sensitivity, dependence on initial condition. Consider the orbit of Hannon map. Now consider the initial condition of this orbit and the another initial conditions. if we take a one initial condition as a x is equal to 0, x within bracket 0, another condition is a initial condition is s dash within bracket 0, then relation will be x dash 0 is equal to x within bracket 0 plus sx 0. It means relation is there. Finally, the words initial conditions are a bit misleading. A typical small disturbance introduced at any time will grow similarly. Think of initial as a meaning a time when a disturbance or error is introduced, not necessarily time 0. Initial conditions in chaotic theory, you cannot say it starts from 0. It means it is a time when a disturbance or error is introduced. It is not necessary, it is a 0 itself. And these are the examples of the chaotic theory. If we take the equations and if we take the value of r is equal to 2, things goes like this. If we change the initial condition from r to 2, if we take 3.3, kindly pay the attention that how much difference is there. Things are repeating itself and things are repeating at a fast speed and they look like to be similar, but actually they are not similar. The logistic equation, very simple equation, with this equation, Lorentz has proved the chaotic system, that chaotic system can be generated with the precise conditions. And again, I have taken the equation r.3.5. This is the, you can say, compare with the previous slide also, like this, 3.2, 3.3, then I take a 3.5, the things are like this, and if I take a 3 is equal to 3.9, and look like this. With things are repeating itself with a minor change in the initial conditions. And another is a bifurcation diagram of a logistic equations. And this can go on repeating itself from starting from 1 to 2, 2 to 3, 4, 5, 6 like this. And it is a deterministic. The overall basic idea behind these logistic equations are that these equations stated by the Lorentz are used for the generation of the chaos. Another example of a chaotic system is the weather. Lorentz has used this concept for the weather forecasting. It is one of the very important applications of the chaotic system also. Difficulties in predicting the weather are not relating to the complexity of the Earth's climate, but to chaos in the climatic equation. And for this, Lorentz has generated this one, and he proved it like this, that this is the solution that to some extent the generated chaos can be used for the weather forecasting. And nowadays chaotic theory work is also used in solar systems. On a sun system, on a sun surface there are small black holes. Lot of energy is liberated, 6,000 centigrade. And if we are able to predict, if we are able to exactly predict the emission of the heat energy from the sun, then the things would be very, very clear. And it will be able to help us in for agriculture and other developments. So solar activities, lot of work is going on with the help of the chaotic systems. Because at the surface of the earth, surface of the sun, chaos is generated, and this chaos can be studied continuously for the prediction of the solar sun energy, like heat energy, thermal energy liberated from the surface of the sun. It can be understood with the help of the chaos. And this is the graph. And the one very important application of the chaos is found in the fluids. The tsunami and other so many tornadoes, they come in the sea and cause a lot of energy loss and human loss. They can be equally predicted with a continuous study, and chaos is going to play a very vital role, because the waves on the sea, they continuously create a chaos, they generate a chaos. This generation of chaos, this data has to be collected and it will help in the turbulence of the fluid. Now the population growth is concerned. As per the population growth is concerned, it is very useful for the population growth. Population of any particular area can be studied from this. And the logistic equation xn plus 1 is equal to rxn that is within bracket 1 minus xn, is a very simple logistic equation. With this logistic equation, chaos is generated and the population growth of any particular area can be studied. Now these are the few applications of the chaos. In fact, chaos has so many unlimited applications, but in selected fields, because it's a new branch and lot of work is still going on. The main application it is for steel smelting. Chaotic PWM scheme for AC motor to significantly suppress the harmonic peaks. Prediction of wind power generation based on the chaotic phase space. Reconstruction models. Fault diagnosis for analog circuit. In field of a mobile robots for secure communication. In fact, prediction is a forecasting technique for a chaotic data. While chaos places a fundamental limit on long-term prediction, it suggests possibility for a short-term predictions. It has shown that a forecasting approach based on a deterministic chaos can be quite effective in predicting low to moderate dimensionality time series, and this can be done with reasonable amount of data and computer time. An inverse approach to the dynamical system been successfully used to identify chaos in a time series, make a short-term prediction and also some restricted form of a long-term prediction. Team CHUA has presented a numerical algorithm for short-term prediction of a time series based on delay coordinate embedding. Algorithm developed by Wang and Mendel has been implemented by Andrew to predict the chaotic time series. It has been concluded that the noise level increases, the predictive properties of the fuzzy controller are downgraded. A distance function has been used to allow us to apply the theory to temporal pattern recognition. In fact, as per this chaos is concerned, it will found application unlimited in all the fields. And this is what I am simply explaining to you is simply a tips of iceberg. Very, very basic concept. And in the coming time you will find out chaos is going to enter in every field and there will be unlimited applications. And especially in a secure communication, which is the topic here today I am going to discuss with you. Next slides. For a secure communication in the field of mobile robots, the chaos is going to play a very, very vital role. And how it is, just I will explain to you in my future slides. Now, up to now, I have tried to explain you give you the overall picture of the chaos. Now, in my coming slides, I will take my yesterday lecture, that is Memristor, and the idea of the chaos. I will make these two concepts, and now I will move further to the basic idea for the secure communications. So, in a chaos and CHUA'S circuit, Professor Leon CHUA has given the idea of the memristor, which I have already explained to you yesterday. And this memristor is also called by one renowned name, that is CHUA'S diode. Memristor is also called by the name CHUA'S diode because CHUA, as I told you, father of the memristor concept, and he have given the idea of the memristors. So here I am going to make these two circuits and move further. Now, chaos and CHUA circuit, this I have already explained to you. He was a professor in University of California at Berkeley, and beside RLC he have given another nonlinear resistor, and this RLC and memristor are three basic concepts. Now that concept of memristor will be again repeated here. With those concepts, Professor Leon CHUA has generated a chaos. Kindly look towards this diagram. And here is A is a Professor CHUA'S circuit and Professor CHUA'S diode. Professor Leon CHUA diode is a memristor here. And generation of chaos with a limited and predictable condition is the main concept. If you are able to generate a chaos with your known conditions, then you can use it for a multiple applications. Professor Leon CHUA has given the idea of the memristor. With his idea, he have taken the concept of this LORENZ, Professor LORENZ of chaos, and he have generated chaos with his memristor, with his chaos circuit, and these are the result. And these are the very simple equations of Professor CHUA'S circuit using a memristor. and he is able to generate the chaos. And this concept of Professor CHUA'S circuit, the chaotic signals are generated with the known conditions, and these known conditions we will use for a secure communication. Another very scientist, very well known, who have worked in secure communication is a Rosler. Professor Rosler has given his equations. With these equations, he have generated the chaos. And after Professor CHUA, after Professor LORENZ, Professor Rosler give his equation. With this equation, he is able to generate a chaos within known conditions. Another, the scientist named Mulisim, he worked on a Rosler equations, have designed a model on a Rosler equation. The model, the circuit diagram is given here. You can also work on it with the stated conditions. With this circuit diagram, he is able to generate the chaos. What I want to convey you, that generation of chaos is a very big thing. It is not a small thing. You cannot generate a chaos because every system cannot predict a chaos. Only a limited circuit with a stated condition, they can generate a chaos. So generation of a chaos is one of the major things, because if you are able to generate a chaos with a non-initial conditions, you can use it for a multiple application for desirable results. Now we have discussed this Mulisim equation of Rosler with respect to time, and this is the result. You can see from the diagram the generation of chaotic signals, and these chaotic signals are defined. Their input parameter, we know it. If we know the initial condition of a generated chaos, we can control the chaos. We can control the chaos as per the requirement, so that we can get the desirable output result. We can work on it. But if the chaos is generated by the nature and if we do not know the initial conditions, then I don't know. If we are not able to control the chaos, then how we can apply that chaos for multiple applications? So if we want to use the chaos for a technical unlimited application, it means generation of chaos is very important. And in 2012, I have got the opportunity to chair a technical session in Las Vegas, USA. And there I met number of professors in University of Nevada in Las Vegas. There the main concern was that chaos is proved, chaotic theory is proved, but the generation is a very big problem, and that also with the specified parameters, and that also with the control conditions. Things are very easy to say that you can generate a chaos, but the main thing is how you control it. Its parameter has to be controlled. Only then it is useful. Otherwise chaos is everywhere. And this is a Rosler attractor obtained by plotting X and Y. Now please pay your attention here. I am just going to summarize my lecture of yesterday and today with the main theme. The title of this work, which I had an opportunity to share with you, my work which I am working from last 5 years, that is secure communication. I have tried to explain Memristor, given by the idea Professor Leon Sua. Then I have taken the concept of chaos. Now the question arises, Memristor, as per the India is concerned, I don't think, as per my knowledge, any actual research work has started, neither in a chaos nor in a Memristor. I am working theoretically. The question arises, the concept of Memristor, if it is adjusted with the chaos concept, we can apply this for a secure communication. Means step number 1, that is, with the Memristor, you generate a chaos. And the generated chaos with a specified input parameters. And this generated chaos should be in a controlled manner. So in any communication system, as the diagram shows, transmitter, receiver and transmitted signal. At the transmitter, it has to be chaotic. And how it will be chaotic? We have to generate chaos. I have taken the example of CHUA'S circuit, which I have just in my previous slide explained to you. The chaos is generated, then the message signals. It means in communication, the very basic term is modulation. And as I just repeat, modulation is a process by which one of the component, whether amplitude, voltage, amplitude, frequency or phase, can be varied with the instantaneous value of the modulating signal. So CHUA'S carries the signal, so the carrier signal will be CHUA'S signals, and another one will be modulating signals. The carrier signals will be CHUA'S signals, and they will be modulated, and similarly they will be transmitted as in the other simple communication system. At the receiver level, the same signal will be received. Here also CHUA'S will be generated with the initial condition, its result can be get. So the basic idea is, when you convert your important message, when you convert the desirable data with the help of a CHUA'S, it will be very, very difficult for the third unwanted party to stall it, to copy it, because they will be not able to distinguish out of the CHUA'S, out of the disorder, whether it contains a useful information or also not. So this is the basic work behind this idea, that we have to generate a CHUA'S, and from the generation of the CHUA'S, we have to modulate it, we have to transmit it, we will receive it, we have to demodulate it. And nowadays, for example, tornado comes, if a strong waves comes, nobody will be able to distinguish that out of this disorder there might be some useful information. So it means it is a security point of view is far better if we applied a CHUA'S to any communication system. It is early stage. In coming time, lot of work will be done on it. As I told you, in Las Vegas, in University of Nevada, USA, I have gone there, I visited there, I have shared my works. There people are working on it. In January 2015, I had opportunity to interact with scientists in Bangkok, Thailand. There also, people are implementing this technique of generation of CHUA'S in a in communication system. Input of the transmitter is never equal to the output of the receiver. You take any communication system till date, you will find out improvement is required there. And CHUA'S will produce, in the early experiments, CHUA'S has proved that here noise will be controlled to bit length, and signals are secure also. So in this lecture, the summary goes like this, that with the help of memristors, with the help we generate a CHUA'S, and with applying a modulation technique, we will generate a secure communication, and it will be also a controlled noise. So the output or the coming time, the communication system would be far better. And this is the conclusion of this complete work, that CHUA'S has emerged as a multidisciplinary science, and since its appearance in simple electronic circuits, the study of circuit has received enormous interest in science and engineering. Electronics networks have become an ideal tool to study chaotic dynamic and control. As all chaotic circuits have several common properties, so the method used to study a control chaos in this network are applicable to many diverse physical systems. And this is the references. At last, I would like to add one thing, that maybe in next decade, new subjects will be there for these communication engineers, for IT people, ICT peoples, for computer engineer, electronics engineer. With this lecture, I would like to end that this computer engineer, they are computing in only binary, 1 and 0. But with 2 this state, you have worked so much. You can have an idea in your mind, if there are dozen of states, if there are 100 of states, if between 1 and 2 there is 1.1, 1.2, 1.3, something like this, then what will be the advancement in the engineering? Similarly, in mobile communication engineering, the CHUA'S will play a very vital role. CHUA'S theory has widely applicability in modern science and technology era. Communication, fault diagnosis, and nonlinear control may see as a paradigm shift, as will several other engineering areas. Research and study in this area can be extremely useful for the field of engineering. In this field, lot of work is still required to be done. The work carried out in this research work will be guiding feature for the scientists working this field. In summary, as quoted by Henry Adams, chaos often breeds life when order breeds habit. Chaos often breeds life when order breeds habit. Thank you very much for such a nice patient hearing. Gentlemen, I have given you two ideas, Memristor and chaos, for future MTech thesis, PhD thesis, and you will find out at present very few people are working in this field. Thank you very much. You are invited for questions. Any question, please?
Yes, sir. How chaos theory differs from probability theory?
Basically, chaos theory is a very big part. Probability, just a small part of it. Both are interrelated, but chaos, lot of work has to be done it. It has to generate. We have to generate chaos with a limited and stated parameters, because these generated signals will be applied to a determined, to a predictable application. Probability is a very small part. It cannot cover that much. And chaos theory is a very big concept. Thank you.
What
Next question, please.
chaos-based simulation tools are available for prediction of solar energy available at a location?
Actually, this is a very early stage. Lot of work is going on, but till date we cannot specialize, because as I told you, if you refer my yesterday lecture, you will find memristors. Even memristor also, it is early stage. We cannot get that memristor. Now the question arises, generation of the chaos. So many people are generating chaos. Generation is not that difficult. But if a limited generation with a non-input parameter, and that has to be applied to a particular application, as per the solar is concerned. We know it, lot of energy is emitted. Lot of energy is emitted from the black holes on the sun is there. 6,000 centigrade temperature, and they are reaching to the world, Earth, at a different phase of time in different 12 months. But the chaos is there, but how to study it? We have to apply different techniques. Models are there. But till date, lot of work is going on. We cannot say that we have achieved something. Well, let's hope in the future result might be there. Next question, please.
When chaos is generated with known specified control parameters, then should it not be called by some other name rather than chaos, say like encryption or disorderly order?
Your question is really good. I would like to appreciate it. You can call it. Who stops you? Because as I told you in yesterday lecture, for new science, new theorems, new laws, nothing is standardized. Even in the memristor also. In Thailand, memristors they are designing memristors. In January 2015 as well as July 2014, again to January 2014, I had visited Thailand, Bangkok. So there are so many companies working on the memristor. The problem arises, there is no standard. Everybody is saying that my work is standardized. So same thing with else. Since it is not developed, it is in developing state, you can call it like this. Next question, please.
What is benefit of chaos in secure communication?
Sir, I am talking to you on a mobile. If others are also copying it, what is the use of it? Now people are hacking system is going on. Other countries have hacked our complete computers. How it can be stopped? Chaos is going to play a very, very vital role. One thing more I would like to tell, in security for a chaos in US, lot of research work is going on for a military purpose. This coding, other countries are working how to hack the codes of the other countries. If you use a chaos, the main thing is you have to generate that chaos first of all. For generation you require a particular equations, and that is not easy work. If you stole the chaotic, if you stole the chaos of other country or other system also, then does it also it means nothing, because you have to extract the information from that very chaos. And the initial condition, its generation is only available with the person who have generated the chaos. Thank you. Next question, please.
For now, those are the questions, sir. We'll just give 1 more minute.
Okay.
So there are no more questions, sir. Thank you very much.
Okay. Thank you. So nice of you.